In theory, a web crawler follows a simple software loop. Download a page, read the links, and follow them. But the chaotic structure of the open internet quickly destroys any script that relies on that assumption. The textbook definition of a web crawler is a system that discovers new or updated content on the web, starting from a known set of URLs. This mechanism provides the raw data for search engine indexing, large-scale web archiving, financial data mining, and automated copyright monitoring. For our design session today, we are building a search engine indexer with a specific load, processing 1 billion HTML pages per month, capturing new or edited pages while ignoring duplicate content. We face two severe environmental constraints. First is robustness. The crawler must survive malicious traps, broken HTML, unresponsive servers, and corrupted links without a system-wide crash. Second is politeness. If our system hits the same website with too many concurrent requests, we risk launching an unintentional denial of service attack on that host. Achieving this level of fault tolerance and precise rate limiting requires moving beyond single scripts and designing a massively parallel, distributed architecture. A 1 billion page monthly requirement translates to a processing rate of roughly 400 pages per second. However, since traffic spikes are inevitable, we must provision for peak capacity, doubling that requirement to 800 queries per second. The true bottleneck is the data's weight. Assuming an average page size of 500 kilobytes, 1 billion pages generate 500 terabytes of data monthly. Over a 5-year retention span, that compounds into 30 petabytes of required storage. At a 30 petabyte scale, aggressive deduplication and processing efficiency are the difference between a functional index and a bankrupted data center. The naive algorithm approaches this linearly: maintain a list of URLs, download the page, extract the links, and add them to the bottom of the list. On the live internet, this script stumbles into spider traps, an infinitely deep directory structure designed to lock the crawler in a permanent loop. We must break that loop into a modular pipeline, starting with seed URLs. Because the internet is too vast to map from a single point, we distribute seeds across different domain localities to maximize our starting footprint. Instead of a basic text list, extracted links feed into a dedicated component called the URL frontier. It acts as the scheduling brain. It's a complex queuing structure that determines the priority of each URL and enforces politeness limits for specific domains. Isolating URL management inside the frontier separates the state of our crawl from the mechanical risk of fetching data over the network. Next, the URL frontier dispatches a link to the HTML downloader. But translating domains to IP addresses creates a hidden bottleneck. If we rely on synchronous DNS lookups, latency stalls the fetch worker. To maintain our 800 QPS peak, we decouple a custom DNS resolver. This allows thousands of parallel threads to operate without waiting on individual translations. Once the page is retrieved, we face the next threat: internet garbage. Malformed HTML and malicious scripts will crash any parsing logic that isn't isolated. We pass the raw data to a strictly isolated content parser. If a severely corrupted page causes a fatal error, it only crashes that specific parsing thread, leaving our network fetching unaffected. This separation protects the most resource-intensive part of the system, network I/O, from the internet's malformed data. Since nearly 30% of web pages are duplicated content, storing every parsed document is mathematically impossible for our 30 petabyte budget. We establish a defensive checkpoint immediately after the parser: the content scene filter. To compare documents at scale, we compute cryptographic hashes of the HTML text. If the hash matches a record already in the system, we know we've processed this content elsewhere, and the page is dropped. Only unique content passes through to content storage, which uses a hybrid approach: fast memory for popular data and durable disk drives for the bulk 30 petabyte set. Eliminating duplicate data before it reaches the database is the only way to keep our storage costs under control. With the HTML stored, the pipeline moves to the link extractor to find the next batch of targets. The link extractor's primary task is normalizing relative paths into absolute, standardized URLs that our system can accurately track. These standardized links enter the URL filter, which strips out blacklisted domains, unwanted file extensions, and formatting errors. To close the final vulnerability, infinite graph traversal, we introduce the URL scene checkpoint. This component uses a massive Bloom filter and memory-backed hash table to check if we have ever queued or crawled this exact link before. We save only unique URLs to URL storage to persist the crawl state, then route them back to the frontier to restart the cycle. This strict URL deduplication stops spider traps, ensuring the crawler only moves forward into unmapped territory. Putting these pieces together reveals a complete 11-step discovery cycle. A seed drops into the frontier, is fetched by the downloader using IP data from the DNS resolver, and validated by the parser. The content scene check acts as the first gatekeeper, dropping redundant text and pushing only unique pages into storage. The extractor pulls child links, the filter cleans them, and the URL scene gatekeeper drops existing links, routing only fresh targets back to the frontier. Operating at a billion-page scale necessitates an aggressively defensive, highly controlled discovery pipeline designed for constant failure. Failure at either deduplication gate results in either an exploded storage budget or a system locked in an infinite geometric loop. We have successfully protected our servers and isolated the crawl state, but we still haven't solved prioritization or robots.txt compliance. To solve those, we must crack open the internal logic of the URL frontier. We'll tackle that in our next session.